just as a reminder, exam's going to be next Monday. Okay. My plan for today is to go over some aspects of blood pressure regulation and talk about concept of shock and capillary exchange. Okay. I don't think we're going to start blood. We'll go over blood, immunity, and lymphatics. So I would expect the schedule of exams as follows. So you're going to have blood immunity exam. Definitely 100%. Maybe respiratory, but I wouldn't be so positive. And it's possible that we'll bump respiratory to after Thanksgiving. Respiratory is a really small one, like really small. And then renal is going to be, renal reproductive is going to be. Like that's like physically, it's not going to be. So we're going to start our conversation today with a discussion of factors that affect blood pressure. Okay? And so that's going to be one of the niche topics. And I want to break them down into sort of two main categories, right? Factors that affect blood pressure can be changed in a long term, or factors that can be changed in a short term, okay? So to do so, let's figure out what blood pressure is proportional. So basically, what is blood pressure? It's the force that your blood exerts on the walls of the circulatory system. Does that make sense? So, remember I told you about the whole system with the pump, central pump and the pipes. So the stronger your pump pumps, the higher the blood pressure. Does that make sense? So the harder your heart works, the higher the blood pressure. So your blood pressure will be proportional to, first of all, cardiac output. Does that make sense? Now, usually we use the expression blood flow, but if you think about it, what is blood flow? It's the volume of blood per minute. Does that make sense? So we can say, what is the blood flow to the brain? It's the volume of blood per minute that reaches the brain. Okay? If we're talking about systemic circulation, the volume of blood per minute that reaches all tissues is a cardiac output. Does that make sense? Now, second thing, if you ever used a garden hose, you know that if you put your finger at the opening, the pressure will dramatically increase. So if you increase resistance to flow, the pressure will go up. Does that make sense? Okay. Cardiac output multiplied by peripheral resistance. Right? That's basically, and look at this. How we can increase blood pressure. We can either increase cardiac output or increase peripheral resistance, or both. Does that make sense? How can we decrease blood pressure? Decrease either or both. We're good? So we're going to keep it in mind as we kind of go over the factors. Okay? That make sense? All right. So, first, I want to highlight the factors that affect blood pressure in the long term. We'll call them long-term factors. I don't know what I'm compensating for, but I really like it. So one long-term factor, if you think about it, is blood viscosity. And here's the thing, the higher the viscosity, the higher the blood pressure. Because if you need to pump more viscous fluid, you have to develop higher pressure. Does that make sense? Vessels, if you have more pipes, you need to develop higher pressure. That makes sense? And finally, turbulence of the flow, I'll explain it. So, you can ask me, blood viscosity, makes sense? Vessels length, makes sense? Yeah, no, never, ever rephrase your question with the words, it's a stupid question. No, it is not. It's all questions are legitimate questions. Turbulence of the flow. If you go to a river, and like look down from the bridge, you see that where there are no rocks, nothing like no logs or anything. The water flows kind of in a straight line. As you can see by reeds like this little reeds in the bottom of the river, they're all straight. But when it comes down to boulders or logs in the water, you can see all these little whirlpools coming around. So those whirlpools is the representation of turbulence. So for instance, when your blood flows into one straight vessel, it's perfect. When there is a plaque in that vessel, like little bump, or there's a branch of a vessel, like vessel branches out, the blood will start to swirl. That makes sense? That slows down. Now, black hole and long term. You cannot grow vessels overnight. You cannot develop an atherosclerotic plaque overnight. You cannot, unless you do some absolutely crazy shit, you cannot change blood viscosity in a matter of like minutes or hours, or even overnight. It takes a while. That makes sense. Now, next group of factors that I want to put here is kind of, medium. Let me explain what I mean. Blood volume. And I deliberately put factors in a way, if you increase blood viscosity, you increase pressure. You increase vessels, then you increase pressure. You increase turbulence, you increase pressure. You increase blood volume, you increase pressure. Does that make sense? You don't have to think like, what does change leads to? Do I make no? Yes. If there is more turbulence, it will create more resistance to flow, and it will have to pump higher. Look, it will increase resistance, and because it's a systemic parameter, we'll get to this. Give me 1 second. And then you have short-term factors. Say it again. Not overcompensating, just compensating. Yes, because the deal is, let me do this. Let me do this. It's totally fine. It's a really good question, and I'll address this. Okay. So short-term factors that will influence your blood pressure. Where are you, 'Cardiogenic. Okay, and this, because look, peripheral resistance is kind of weak. That's the now, vessel diameter, let me show you what I mean by this. Peripheral resistance is inversely proportional to the vessel diameter, or radius, doesn't it? In the following. So let me address this first. And then I will go over these factors one more time, chatting with you. So if you have a blood vessel with a diameter of, say, 10, then peripheral resistance would be proportional to 1 divided by 10,000. It's 10 in the power. Okay? Now, if you dilate the same blood vessel to from 10 to 20, then peripheral resistance will be proportional to 1 divided by 20 in the power of 4, by the following, which is 160,000. So you dilate the vessel, and the difference between these two is 16. See that? You dilate the vessel 2 times, you decrease peripheral resistance by 16-fold, and vice versa. If you constrict the vessel 2-fold, make it 2 times narrower, peripheral resistance will skyrocket 16 times. Does that make sense? So you can regulate vessel diameter very easily by the smooth muscles that are in the clinical medium. Does that make sense? They can constrict and dilate amazingly fast. We're talking about seconds of response. Does that make sense? So this is the fast. As well as you can change the cardiac health. But look at the responses that we're talking about. So blood viscosity will increase blood pressure by increasing peripheral resistance. Vessels length will increase peripheral resistance, increase blood pressure. Turbulence of the flow. So when we say turbulence increases peripheral resistance and increases blood pressure, this is what we mean. Blood pressure is the centrally regulated parameter. Your brainstem maintains systemic blood pressure. But another parameter that has to be regulated is the perfusion of tissues. The tissues cannot be hypoxic. Does that make sense? Basically, it means that if blood vessels that lead to some muscles start to become a little bit obstructed by plaques, your heart will have to bypass them. Do something about getting the blood to the muscles anyway. And how will it change blood pressure? It will increase it because resistance increases, and to maintain perfusion, cardiac output has to increase. Does that make sense? You good? Okay. So again, what I want to highlight, these factors, they affect peripheral resistance. Blood viscosity is kind of weird. We can count it as affecting resistance as well, because it's so thin. Blood volume is kind of a thing of its own. And cardiac output, well, it's a cardiac output. It's how hard your pump works. Does that make sense? And first, we're going to chat about the changes in how different parameters change in the different blood vessels in a human circulatory system to figure out how we can regulate blood pressure. So we have, as you remember, we have arteries, right? We have veins, and we have capillaries. Okay. So the direction of the blood flow will be this. Does that make sense? Okay. But first, let's address the diameter of the vessel. Individual vessels, individual vessel diameter. Aorta is the biggest artery, right? And then you go from elastic arteries to muscular arterioles. They become progressively smaller, right? So diameter decreases. Then, from the capillaries to large veins, it increases. Again, we're talking individual vessels. Good? Ask me if something is unclear. Now, what about, I'm not going to put it on board, but what about the number of blood vessels? How many aortas do we have? How many, like, massive arteries? Like, how many subclavian arteries do we have? 2, left and right. Make sense? How many capillaries? A lot. Yes. How many arterioles you have? You have a shit ton of arterioles. Does that make sense? So although, look at this, although the diameter decreases, the number of those tiny little blood vessels increases. So aorta may be this big, but that's the cross-sectional area of aorta. Capillary is so small I cannot even show, like 8 nanometers, 8 micrometers in diameter. But if you have like 10,000 capillaries, that's an enormous cross-sectional area. Does that make sense? So cross-sectional area, I'm going to put just area, will actually increase dramatically. So you can think of it this way. It's like a river, okay, or a creek. If the creek goes through a very narrow part, the flow is fast, right? Flow is fast in arteries. So we're going to put velocity of the flow. Okay. It is very fast in arteries. It becomes very slow in the capillaries, and then peaks up in the veins. So capillaries experience the slowest flow. And finally, how does blood pressure change? It doesn't change linearly. So I will kind of give you a bit of a graph. Okay. So you see there is a drop. Pretty steep drop here. See that drop? That's up here. Okay. So blood pressure in your aorta and big arteries like capillary or carotid or brachial, subclavian, axillary arteries. Blood pressure there is pretty stable. Good? when it gets to, even in the muscular arteries, it's pretty stable. When it gets down to arterioles, the smallest vessels, that's when the pressure declines rapidly. Then it declines through the capillaries, and in veins, it kind of goes down. That makes sense? So basically, at the moment when blood enters veins from capillaries, the pressure is 17 millimeters of mercury. The starting point is 120. By the time the blood gets into the right atrium, pressure is 0. Does that make sense? That illustrates another really, really important point. That blood always flows from the area with a higher pressure to the area with a lower pressure. Are you following, Ashley? Any confusion? Mm-hmm. Excellent. Excellent. Thinking about this one? Fantastic question. If we talk about individual vessel, absolutely. But when we use the term area, we apply it to all capillaries. Does that make sense? So think of it this way. If you will compare a pipe like that and a cocktail straw, pipe will have much less resistance. Are you with me? But if you will compare a pipe like that with a flow of, say, water through 10,000 parallel cocktail straws, these cocktail straws will provide an enormous cross-sectional area for the flow. Does that make sense? This is why, and you're absolutely right, although the diameter decreases, the resistance in, and that's a great question, the resistance in capillaries decreases, the resistance in capillaries is really, really small because there's so many of them. Does that make sense? Same goes for veins. They are pretty large, they easily stretch. So the resistance in veins isn't great, so drop in blood pressure is pretty small. Good? That makes sense so far? Better? Okay, good. Now, so blood always flows from the area with a higher pressure to the area with a lower pressure. Kind of long, right? Now, if you think about blood flow through arteries, it's not a problem. If we're talking about going up to the head, and I'm purely anatomical, you know, if we're talking about pumping the carotid artery or, you know, upper extremities, that's not that far. And most of the time, your arms down, so gravity is on your side. Going down is super easy. First of all, your heart pumps, and then gravity pulls. And then capillaries, whatever. But then you've got to have venous return. Again, returning from the head isn't a problem. Gravity. Extremities, we'll talk. Upper extremities, we'll look in a second. But what about the legs? In this case, blood has to flow against the gravity. So, what works? Two things. First, we mentioned muscular part. Okay? When I walk around like this, muscles in my legs, they contract all the time. Not that much, but they do. And when they contract, they squeeze those veins and they kind of push the blood out. And what prevents blood from going down? Venous valves. So the venous valve looks like this. Okay? So blood flows up. If it tries to go down, the valve flaps to prevent it from doing so. Okay? Respiratory valve as well. Now, you would ask people who have to stand for a long time, they get swollen. because the muscles don't contract, there's no pump. The blood starts to pool in the lungs, right? Makes sense? So let's define a couple more things related to the pressure, and then we will discuss how we can regulate it, right? So, few definitions. I'm going to use our standard, classic, 120 over 80 blood pressure, which is considered to be normal. Okay, so 120 is systolic, and 80 is diastolic. Okay, so systolic pressure means that it's a pressure in the system when your heart, and strictly speaking, it's a pressure in the aorta when heart contracts. And 80 is the pressure in the aorta when heart relaxes. Good? So, I'm going to ask some very inhumane questions. Can we measure a blood pressure in the aorta? I'm asking, should we? I'm asking, can we? Yes. You will have to do surgery. You can do it. I don't know why, because you will have to sacrifice the person afterwards. But yeah, you can do it. Now, we don't do it. Measure blood pressure in the large arteries that are as close to the heart as possible. So aorta would be ideal, right? Yes. So we choose brachial artery, which goes through the upper arm. Okay, that makes sense. What would be a better place than the upper arm, closer to your aorta to measure blood pressure? We don't do it for some reason. Yes. Neck would be ideal, but that would be kind of, not a great deal, right? Carotid would be great. So when we measure blood pressure, and you will probably have an experience with sphygmomanometer, right? If you do it an old-fashioned way, you have a cuff, you have a stethoscope. What you essentially do, you pump the cuff so hard that it completely obstructs the blood pressure, completely stops it. So when you listening to brachial artery, you hear nothing. You start loosening the cuff. And at some point, the pressure in the cuff becomes smaller than systolic. You start hearing sounds. Basically, it's a pulse called Kirchhoff sound. You keep loosening it, and at some point, the pressure in the cuff becomes smaller than diastolic. Then you hear no pulse, sounds go away. That's when diastolic pressure is taken. That make sense? Difference between systolic and diastolic is called pulse pressure. And then using kind of 120 over 80 all the time sometimes is inconvenient. So you can replace it with a single number. It's called mean arterial pressure. So what you do, you take diastolic plus pulse pressure divided by 5. Okay. So in this case, it's going to be approximately 93. Okay. Does that make sense? Now you don't need to memorize the numbers. You need to know the formulas here. So I can ask you this, I can ask you this. Just kind of FYI, so hypertension is 140 over 90 and above. Between 120 over 80 and 140 over 90 is pre-hypertension. Hypertension can be primary, which is like overconstriction of blood vessels, atherosclerosis. for some reason increased cardiac output, shit like that. Or it can be secondary when, for instance, your kidneys don't work properly due to the glomerulonephritis with hypertension. Right? That makes sense? So, or you have some weird, you have thyroid problems and you get hypertension. You take care of thyroid problems, you take care of the hypertension. Does that make sense? Yeah, hypertension proves a lot. Okay, you got this. So probably should start talking about the regulation. If you want to, well, we actually, I will try to feed the baroreceptor reflex okay. Then we'll have to go over some stuff. So far, any questions? So let's start. Any reflex, baroreceptor reflex as stimulus, sensor, an integration center, an output, and reflex. Does that make sense? We're going to start, and I want to remind you that when we're going to talk about what happens when blood pressure goes down, and then we're going to talk about what happens when blood pressure goes up. So, blood pressure goes up. Doesn't matter. We're going to start with that. It goes up. So when blood pressure, and it's going to be very excruciatingly detailed, when blood pressure goes up, what happens to a stretch of the blood vessels? Like when there's more pressure, what happens initially to your blood vessels? They get stretched a little bit more. Does that make sense? So vessel stretch increases, and that stretch is sensed by receptors. Which are located in two main places. One is in your carotid sinuses, and two in the arc of your aorta. So there's mechanoreceptors sense the stretch, and they send the signal. They send the signal to the dual vessel. So it's afferent signal to the medulla. And medulla produces several responses. We're going to break them down. There are three main centers. So one, people know the name is Cardiogenic Shock. And again, this is all in the medulla. Okay. Another is Cardiogenic. And the third one is basal nerve. So look at the names of these centers and tell me, what does cardioinhibitory center do? Just from the name, you don't know anything. So go ahead. What? If it's cardio, what does it inhibit? Huh? The heart. Yes, it inhibits the heart. Yeah. Cardiovascular center, what does it do? Huh? Yeah, it speeds up the heart, yes. Vasomotor center, which organ does it regulate? Just organs. Which organs? Tiny little organs. Thousands of them. Vasa. Vasa. Remember? Blood vessels. Okay? So you have two centers that control the heart, one center that controls the vessel. Does that make sense? No, cardioinhibitory center is parasympathetic. 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 Cardioacceleratory and vasomotor are sympathetic. Does that make sense? So, blood pressure goes up. You need to bring it down. Does that make sense? So to bring it down, you need to inhibit the heart. Make sense? So cardioinhibitory center gets activated. Cardioacceleratory center gets depressed. Are we clear? Now, cardioinhibitory center gets activated and it slows down the heart. Cardioacceleratory center being inhibited also slows down the heart. And on top of that, contractility of the heart increases. Does that make sense? Now, I want you to be very attentive. Look, both cardioinhibitory and cardioacceleratory center, they both control heart rate. But only cardioacceleratory center can influence contractility. Does that make sense? What about vasomotor center? Vasomotor center gets inhibited, which leads to vasodilation. I'm going to put it as the vessel diameter. Increases. Does that make sense? Are we clear? I see confusion. Oh yeah. So vasomotor center, that's pretty simple. Vasomotor center is the part of the medulla that controls smooth muscles around the blood vessels. When it is stimulated, smooth muscles contract, and vessels become narrow. Vasoconstriction, right? Diameter decreases. When the center gets inhibited, smooth muscles are not stimulated. They relax. Vasodilation, diameter becomes bigger. Make sense? Let me ask you the following. Heart rate and contractility. Which component of this equation they affect? Just one. Both heart rate and contractility affect what? Here. Cardiac output. So decreased heart rate, what happens to cardiac output? And the contractility goes down, same, right? Vasodilation, which component of this equation it affects? So again, peripheral resistance. So when diameter of the vessel increases, peripheral resistance down. And when these two parameters go down, what happens to blood pressure? Now, let me ask you this. It's really straightforward. If I want to describe how baroreceptor reflex can respond, look up, can respond to low blood pressure, what do I need to do here? Reverse all arrows. Does that make sense? Except for the connector one. So blood pressure goes down, stretch goes down, cardioinhibitory goes down, cardiac-acceleratory goes up, blah, 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 all like completely fluid. So it's super straightforward. Does that make sense? Good. So this is an immediate response. Okay. Now, it's a bit challenging. I'm not complaining. Just trying to kind of explain it. We always in science we take reductionist approach. We try to break processes into steps, which is a bit hard because while we are talking about blood pressure here, blood pressure is a systemic, right? Okay. So at the level of the organism, the cardiovascular system tries to maintain blood pressure. Does that make sense? But at the level of individual organ, the organs and tissues try to maintain perfusion. Does it make sense? Perfusion meaning the amount of blood that goes through a particular organ or tissue. So that's kind of an easy question. What is more important? Maintenance of a blood flow, like baseline blood flow, to a particular tissue, or maintenance of the blood pressure at organism level. Blood pressure is more important. So basically, think of it this way. You have a giant corporation, which is a human body, which has multiple branches. And all those branches are important. But at some point, like in any corporation, like if it's GM, maybe they have some gigs on the side, like tourist business or something, you know? They may have to get rid of the unimportant stuff in case of a crisis. Does that make sense? So same happens to your body. When you are losing blood, for instance, blood flow to some organs that are not that important can be shut down. Temporarily, of course, until you restore proper volume of blood or proper blood pressure. Does that make sense? It may hurt, yeah, absolutely. But for it, you have some organs that are more important than others, heart and brain, right? Like if your intestines or stomach do not get enough blood for a day, I mean, they will get some, but not a lot. You're not going to be comfortable, right? But if your brain doesn't get enough blood flow, you're dead. Okay, so that's kind of, different. Does that make sense? Now that was really a fundamental thing. I want to really keep it here. So I'm going to get rid of this part and chat a little bit about other mechanisms of regulation. First one was chemical mechanism. So we consider this being neural mechanism because mechanoreceptors, they send the signal to the medulla by the afferent neurons. Right? Now, what about chemical? That's pretty straightforward. And again, I want to highlight that we are talking at the systemic level. Okay? So imagine that for some reason, I don't know what that is. For some reason, we have a patient who experiences acidosis, low pH. Respiratory gas that is acidic is CO2. Make sense? So think of it this way. You have a system that is polluted with CO2. Okay? So what you need to do with the blood flow, how do you need to change the blood flow to get rid of that excessive acidity? You have an accumulation of crap in tissues, virtually all of them. What do you need to do? How do you need to change the blood flow to get rid of that pollution cost? Huh? Increase. And if you increase blood flow, what happens to the blood pressure? Does that make sense? So, elevated CO2, low pH, which is acidity, and increased oxygen, only to again, systemic regulation. Does that make sense? Why I point so much attention to systemic? I'm going to ask kind of an offensive question. Do your brains work right now? Hope so. They work pretty hard, right? So they require much more energy, and blood flow is redirected to your brain. Does that make sense? Now, if you would eat lunch and then just sit and watch some mindless TV show without like Transformers, the greatest movie ever, the blood flow would be redirected to your stomach and your intestines, because they will be the most hardworking organs. That makes sense? But it's a zero-sum game, because whether now or after lunch, your blood pressure will be 120/80. So you see, the flow will be the same. It will be just redirected based on the needs. Does that make sense? So in this case, we are talking about the systemic changes. When CO2 concentration increases everywhere for some reason, when pH decreases all over the body, people develop acidosis as a result of diabetes, stuff like that. Make sense? It's chemical. Now, chemical mechanisms and baroreceptor reflex, they are relatively fast mechanisms that regulate blood pressure. That makes sense? Now, what about not so fast? Look what I put here. Blood pressure. Right? So there are two absolutely fascinating renal mechanisms of regulating blood pressure. First is direct renal mechanism, which is astoundingly simple. When the blood pressure, I'm going to feed it in several levels. When the blood pressure goes up, what happens to the blood flow to the kidneys? What happens to the blood flow to the kidneys? When pressure increases, goes up? Yeah, absolutely. Now, as more blood goes into your kidneys, what happens to the amount of urine that you flow? Yeah, of course, the kidneys is a filter. The more fluid you pour in the filter, the more flow through you're going to generate. Does that make sense? When you generate more urine, what happens to the blood volume? Of course, you pee the volume out. Does that make sense? And as blood volume goes down, what happens to the blood pressure? Make sense? Basically, physiologically, let me put it this in perspective. Let's say we're going to do a water drinking challenge, which I seriously disapprove of. But let's say I drink a gallon of water. What's going to happen to my blood pressure? Immediately after. It's going to go up, of course, because my blood volume goes up. And what's going to happen to me 15 minutes later? I'm going to run to the bathroom, and I'm going to start peeing all that fluid. And my blood pressure will go back to normal. Does that make sense? Clear? Good. There's a direct renal mechanism you can realize. Using food. This is absolutely fascinating. It is called renin-angiotensin aldosterone system. Okay, and you've heard about it. We're talking about it actually, strictly speaking, third time. Okay, we talked about it twice in endocrine. So it all starts, and importantly, indirect renal mechanism responds only to the low blood pressure, only low. So for instance, in case of direct renal, you can flip all the rows, all the arrows, no problem. In case of receptor reflex, you can flip all the arrows, no problem. In this case, the only stimulus is the low blood pressure. It is not involved in responding to high blood pressure. Does that make sense? When the blood pressure is low, the kidneys produce renin. Now, renin is an interesting hormone. It is a hormone that is an enzyme at the same time. So what renin does, look, it stimulates the conversion of angiotensinogen produced by the liver into angiotensin 1. Does that make sense? Now, angiotensin 1 gets converted into angiotensin 2 in the lungs, right? By the, actually, hold on a second. Gets converted into angiotensin 2 by a special enzyme called ACE. Angiotensin converting enzyme, which is an enzyme. And then angiotensin 2 stimulates production of aldosterone that you may remember as the hormone of the adrenal cortex. Okay? Aldosterone leads to increased sodium retention, which leads to increased water retention, which leads to increased blood volume and increased blood pressure. Okay, so let me guide you through this schematics. And I strongly encourage you. I want to do this as a dialogue, okay? So you're more than welcome. You're like, I want to see that you understand what is here. So, when blood pressure is low, what is produced? Where? What does renin do? It transforms angiotensinogen, produced from the liver, into angiotensin. You good? Enzyme produced from the lungs called angiotensin converting enzyme, or ACE, converts angiotensin 1 into what? angiotensin 2. And angiotensin 2 does what? It stimulates the release of aldosterone from adrenal cortex. Aldosterone causes what? Sodium retention. Remember, water follows sodium. So start keeping more sodium in. That leads to water retention. That elevates blood volume and blood pressure. Does that make sense? Excellent. I already asked this question when we talked about it. Just what if we inhibit aldosterone function? What if we inhibit aldosterone function? What's going to happen to blood pressure? Huh? Yeah. And it's actually one of the really effective drugs that they used to treat hypertension. They're basically diuretics. You produce more urine. Okay. Now, the one that I really wanted to talk about is angiotensin converting enzyme. One of its forms, ACE2, FYI, just FYI, it's not for these. ACE2 is a receptor for coronavirus. It is. Without ACE2, coronavirus cannot infect. We'll have ACE2. In the lungs, this is why an infection happens in the lungs. Okay? Now, second question. What if we inhibit ACE? What's going to happen to your blood pressure? It's going to go down. Those are called ACE inhibitors. Okay? And one of the first released on the market is Capillary, which is still used. The story of development is fascinating. So I'm going to put down. I'm more acute. Look, I'm not looking for you to memorize the name of the drug. I want you to understand the mechanism. So, captopril inhibits ACE. Okay. Now the story was fascinating. One of the main symptoms of when people get bitten by a venomous snake, bear with me, a viper, specifically one of, a viper family, they die of a shock, a rapid drop in blood pressure, like serious drop in blood pressure. Okay? So scientists got interested, thinking, okay, we can kind of figure out what happens and use whatever is in the venom to not cause a drop in blood pressure, like significant, but to lower it down, So they managed to identify a compound in the venom of this viper that is responsible for that drop in blood pressure. And some modifications. The folks that did that actually got the Lasker Award, which is like second to Nobel Prize in medicine. It's super great. Okay. But I want to ask you another question. So now you know that a patient who was bitten by a viper will experience the drop in blood pressure. And presumably, you already squeezed the blood out of the wound, shouldn't suck it out because there are many wounds involved. Like you did all the regular stuff, but you are about to drive the dude over to death to a hospital, but it's going to take some time. And pressure keeps falling. How can you kind of stabilize? It's very unconventional question. How can you stabilize that patient? What should you do? Like you have nothing. You have a car. You have a car, you're about to drive the person. You are like not in the completely remote setting, say you like on a highway. Ohio Turnpike. So you're like driving from Newton Falls all the way to Cleveland, and you are on the turnpike. Where should you make a stop? You need to increase blood pressure, right? What should you? It's a food item. They will need some water. That's one of the ways, but it's going to take a while. What can you increase? Almost like this with a food item. Can't hear. Any stimulant. Red Bull, coffee, any stimulant. Okay? It doesn't mean that they can survive on that, but at least you charge their heart enough so they don't go in a complete cardiogenic shock. You see what I'm saying? So that's kind of an idea, and that actually is kind of a connotation. If you have a coffee, Red Bull, anything that will stimulate, sure, that'll work to keep them from completely dying in their heads before you get into that. Make sense? We talked about measurements, hypertension. Here's the deal. We're going to talk about shock before the break. And I also really wanted to say how you can measure pressure in the mouse. You can measure, well, yeah, I can start from the right. I can actually, are we good with bar receptor? Okay, so you can, so when I was working with mice, you can actually measure blood pressure in the mouse in the blood vessel. So usually doing it in the throttle. You put a probe in the throttle, but it's the last thing that you can do. You have to sacrifice it. If you want your mouse to survive, but it's insanely precise, okay? But if you want your mouse to survive, there are devices. I saw one. It is super cute. It's a device to measure a blood pressure in the mouse in the tail artery. It's a tiny little cup that you put at the base of the tail. And it just works just as regular sphygmomanometer. It pumps it and then like sounds all that crap. The only problem is to hold the mouse, right? So you put the mouse in a special tube, so it's restraining, but mice don't like to sit in the tube. So an important part of the device, until like it was standing next to me, it was an exhibition. An important part of the device is the little fan that blows air into the mouse face, because that kind of calms them down, and then your readouts are correct. And the whole thing is supposed like a couple of grand. So it is kind of expensive. But it was lovely. If we wouldn't do the terminal surgery, we were doing like our mice were done surgery. So, shock. Three types. Hypovolemic, cardiogenic, and circulatory. Now, while the origins are different, the result is the same. So let's start with hypovolemic as an example, and you will see why result is the same. So hypovolemic shock means that blood volume is dramatically down. So basically, it's blood volume. Okay? That makes sense? So let's say you lost a lot of it, like 2 liters. So your blood volume is substantially down, which means at this point, blood flow, and I mean like you didn't just donate blood 4 times over a span of a month, recommended, but you really like you bleeding out of an artery, you losing a profound amount of it. So blood volume goes down, okay? Which means blood supply to the heart goes down just because you don't have enough fluid. Make sense? means your cardiac muscle does not receive sufficient amount of oxygen and nutrients. How do you think your muscle in the heart is going to beat if it doesn't receive enough oxygen and nutrients? Slowly. If your heart beats slowly, it happens to your cardiac output. It goes down. When cardiac output goes down, it happens to your blood pressure. It goes down. When blood pressure goes down, it happens to the blood flow to the heart. It goes down. When blood flow to the heart goes down, what happens to the cardiac effort? It goes down. What happens to cardiac output? It goes down. It all goes down. It constantly is going down. Does that make sense? Look at that. Okay? Cardiogenic shock. That's super simple. Your heart fails. So I don't know. Cardiac output isn't just completely off. Make sense? Same story. Down, blood flow is down, cardiac capacity, competency goes down, cardiac goes down, blah, blah, blah. It's all positive feedback. Look at that. Now, that is usually a heart failure myocardial infarction. Okay. Or, sometimes just heart, like if somebody had several myocardial infarctions and the cardiac muscle is, like half of it is gone, what can you do? That's it. And circulatory shock is vasodilation. Now, what if all your blood vessels, all of them, all that can do them, all arterioles, all muscular arteries, even some large veins, what if all of them suddenly dilate? What happens to peripheral resistance? It goes down. And it goes down so much that blood pressure goes down with that. And it goes down so much that blood flow decreases so dramatically that your heart can. Same story. You see, they all converge at the fact that at some point heart ultimately fails. Does that make sense? This can happen in two main cases. One is anaphylactic shock, say allergic response, and two in sepsis. Now, in sepsis, the response is actually dual. So when people experience sepsis, or some folks call it septic shock, what essentially happens is so when you have a wound, the skin around the wound is red, right? Because of vasodilation due to the inflammatory cytokines. When you have sepsis, you have a systemic inflammation in everything. Does that make sense? All your blood vessels start to dilate, so you experience circulatory shock. And on top of that, all your blood vessels become extremely permeable, and plasma starts to leak massively from the blood vessels into the tissues. So you experience hypovolemic shock. Does that make sense? Now, if someone has hypovolemic shock, low blood volume, what do you need to do as a healthcare professional? Immediate response. Get them moving. You don't really need to give them blood. You need to give them IV fluid. That's it. Blood will come later. At this point, because you don't need to cure them. Your goal is not to let them die. Does that make sense? So this is why it's IV fluid. Make sense? In case of circulatory shock, that is a little bit more complicated. Although if you think about anaphylactic shock and you have some experience with it, you will answer. What do you need to do? How do we treat anaphylactic shock? What do people who are epinephrine. Epinephrine, right? Epinephrine is sympathetic neuromediator. So epinephrine will basically charge vasomotor center, and blood vessels will constrict. Does that make sense? Cardiogenic shock, you can do epinephrine. Speaking of which, did you watch Pulp Fiction? No? Watch it. Good movie. There is an episode when Uma Thurman character, thinking that she is about to snort cocaine, snorts heroin. Cocaine is a stimulant, while heroin is a depressant. So she basically delivers a really powerful depressant straight into the brain. And that shuts down, that's all physiologically conceivable. Apparently that eventually shuts down her heart. It's totally possible. It messes up with cardioacceleratory, cardioinhibitory centers. Yeah. That makes sense? So the next scene, sorry, spoiler alert, but John Travolta's character does an epinephrine shot in the heart. Epinephrine shot, fine. Heart, you don't really need to do it. IM or IV would work, just to start it again. Because that basically it's like an adrenaline kick. Does that make sense? So yeah, that, except for this part, it's physiologically considered. Okay, make sense so far? Now, another thing that so cardiogenic, if it's not like a complete heart failure, that may work as well. Now, another thing that I want to, and obviously, sympathetic system increases blood pressure, parasympathetic system decreases. We already covered it in the baroreceptor effects. But there is something else I wanted to related to blood pressure. First of all, when you exercise, your blood pressure increases. Normally. Why? Which component? Cardiac output. Now, it increases for two reasons. First, the heart rate goes up. And second, your end-diastolic volume goes up. Because when you exercise, all this muscular pump moves the blood through the veins into the right atrium. So your venous return goes up. Does that make sense? That's like really important to understand. Your venous return goes up. when contractility goes up, essentially it squeezes more blood out of the heart. So your ESV and systolic volume goes down. So cardiac output increases for increased heart rate, elevated end diastolic volume, and decreased end systolic. Does that make sense? And I want to make clear. So you should be able to make like this inferences basically. If we expand this, blood pressure is heart rate So if I ask you how elevated EGB, changes blood pressure, you think, oh, higher EGB means higher blood pressure. Does that make sense? Stuff like that. Okay. Last thing I want to talk is about the response to blood loss. Not terrible blood loss. Let's say you lose 2 pints of blood. Okay. So it's like 2 blood donations. Which, by the way, would be absolutely like a slip. So if you lose 2 pints of blood, and then blood, hemorrhage stops, you don't bleed anymore. That makes sense? So my question is, let's figure out how you're going to look, what you're going to feel. So you substantially reduce your blood volume. Does that make sense? Which means your systemic blood pressure went down. That makes sense. What will be a compensation of your cardiovascular system to bring your blood pressure back up? First of all, an immediate response. what will happen? An immediate response. An immediate response. Don't look. We're figuring it out. There are no wrong answers. We're figuring it out. Come on. Say again? Increases or decreases? Decreases. Your vessels start to constrict, right? Because if they constrict, peripheral resistance goes up and blood pressure goes up. Does that make sense? All of them? Do all of them constrict? Which ones don't? Or which ones? What is the not? What at this point you lost 2 pints of blood? You're like, almost died. What are the least important organs in this point? While you are en route to the hospital? Bingo. Forget about digestion. What else? Huh? They're not right, but they're not taken along. So sorry for being so blunt, but if you're a man, don't count on the bone. Go ahead. What else? Do you need kidneys? No. So your blood flow to the kidneys will go down. And if blood flow to the kidneys goes down, what happens to your output? Goes down. You're not going to for a long time. What is another organ that you completely forgot about? That you're not really caring about at this particular time. You literally are looking at this organ. It's also an organ system. Yes. Blood flow to the skin will go to practically zero. Does that make sense? How will it make you look? Pale, yes. You're going to be pale. And since there's no blood flowing to the skin, in terms of the temperature, how are you going to feel? Yes. You're going to be pale. You're going to be cold, right? You're not going to pee. That's all vasoconstriction. Does that make sense? I'm sorry about that. Now, can you change cardiac output? Sure. What's going to happen to your heart rate? It's going to skyrocket. It's going to go up because that's going to be the adaptation of your heart. Does that make sense? When you lose blood, your heart is going to start pumping faster to compensate. So you are, by now, cold, pale, tachycardic, and not peeing. Now, in medium-term perspective, can you increase your blood volume? You're already doing it. You're not peeing, right? What else? Well, you can do IV. Now, how can you increase the blood volume? Very simple. And what feeling tells you that you should drink water? Not feeling. You're not feeling dehydrated. What do you feel? What's the English word for it? Starts with T. Thirst. You're feeling thirsty. Yes. So you are going to be thirsty. If you donated blood, you are feeling thirst after the donation. Not that much, but you are feeling thirsty. Okay. So thirsty, cold, pale, tachycardic. Okay, not peeing. And actually, this will be engaged. So your renin-angiotensin aldosterone system will go really. Your aldosterone levels will go up. There's another hormone that is used that prevents you from peeing. I don't know if you remember it or not. It's released from posterior pituitary gland. Anti-diarrhea. Remember that? antidiuretic hormone, and actually ADH not only prevents you from peeing quite literally, but it also will stimulate thirst. Okay. And then when you drink water, you compensate, blah blah blah, and you get better. Does that make sense? And usually, if you lose blood, you're pretty freaking stressed, right? And stress will stimulate the release of epinephrine. And epinephrine will additionally keep heart rate, will increase contractility, all that kind of stuff. Lead to vasoconstriction. So this is why I say, we try to break it down to individual responses, but it's a whole complex. Make sense? Okay. We're going to take a break. I'll come back, talk about tissue perfusion and Cavular Exchange. So now since we have discussed, and we're going to finish it, we have discussed systemic regulation of blood pressure, okay? Like the corporation, okay? Now we're going to talk about the regulation of the blood flow through individual sort of organs. Does that make sense? So here, so this we encountered, I think we encountered this first time, sort of a regulation opposing goals of the systemic regulation versus local regulation. So think about an organ, say a stomach. There's a certain amount of blood that goes to the stomach, right? And blood vessels that supply blood to a stomach, their goal is to maintain perfusion, the blood flow, constant. Are we clear? Or, not necessarily constant, matching the needs of an organ. So for instance, when you are sitting and listening to me, blood flow is directed mostly to your brains. But if you would be running or lifting weights, blood flow will be directed mostly to your muscles. Does that make sense? So because your muscles would require more nutrients, more oxygen, whatever. Make sense? So, and as we already discussed, when you experience, blood loss, then your organism kind of chooses, heart is important, lungs are important, brain's important. Skin, kidneys, digestive system, it can wait. Okay? So, let's talk how a tissue regulates the blood flow. And it's really kind of straightforward. So there are two types of controls. One type of control is myogenic control. Hygienic controls are pretty straightforward. When blood pressure, and we're talking about normal fluctuations of blood pressure, changes, when blood pressure, for instance, increases, what happens to the vessel stretch? It increases, yeah, vessels get stretched. Okay. Now, when vessels stretch, what happens to the diameter? Increases. When diameter of a pipe that supplies a particular tissue increases, what happens to the blood supply, blood flow? Increases. Now you need to reduce it back to normal, right? So what do you do? Vasoconstriction. Does that make sense? So again, and for some reason, systemic blood pressure changes, it spikes, okay? Blood vessels become stretched out. They become stretched out. That increases blood flow. In response to increased blood flow, blood vessels constrict, reducing blood flow to a normal level. This is called hygienic. And, you know, if blood pressure goes down, stretch goes down, diameter of the vessel goes down, blood flow goes down, then vessels dilate and blood flow increases. Clear? Now, what about metabolic force? That's even simpler. If you have a part of an organ that has elevated CO2 or acidic or reduced oxygen, all of this increases local blood flow, increases tissue perfusion. That makes sense. So now let me write down one equation that you are familiar with, actually. What is this? This is an equation, chemical equation, for which process? We discussed it a couple weeks ago. More broad. Yeah, glycolysis is a part of this whole process. It's a cellular oxygen, cellular respiration. Make sense? So in cellular respiration, and what do we need this process for? To generate which molecule? Why do we respire? To burn glucose? Well, yeah, but what's the goal? What's the big sort of outcome? Does this process produce energy? And which molecule is the energy molecule? ATP. So we need this process to make ATP to fuel cellular processes. Good? Got it? Awesome. So in order to fuel cellular processes, we need to burn glucose using oxygen, generating CO2. Make sense? The more metabolically active tissue is, like it works really hard, the cells work really hard. Does that make sense? The more intense cellular respiration is going to. Does that make sense? So in more metabolically active tissues, you're going to use more oxygen and you're going to produce more CO2. Am I clear? So in metabolically active tissues, you're going to use more oxygen. So the level of oxygen will be reduced. And you're going to generate more CO2. Does that make sense? And since CO2 and lactic acid that's produced during fermentation are both acids, pH is going to go down. Does that make sense? So high CO2, low pH, low oxygen is basically a sign of a metabolically active tissue. And metabolically active tissue needs more blood to be supplied, right? To take this crap away and bring in more oxygen. Are we clear? I just want to explain the very physiological level without any formality. We got it? So all of this will increase blood flow. Does that make sense? Now, let's talk about some tissues. We're going to talk about, I don't know, boring tissues first. So muscle. Mostly metabolic. Muscles is actually a poster child for it. Okay? Does that make sense? Like, seriously, when you start exercising, your muscles produce a lot of CO2, pH starts to get down, oxygen starts to get down, right? So you need more blood. Blood flow can increase tremendously. Good? In the skin, it's mostly temperature regulated. But actually, there is some significant metabolic responses. So if you will, like put some clamp on your finger and leave your skin without blood supply, you remove it, the blood flow will increase dramatically because of accumulation of CO2. Does that make sense? Now we're going to get to more interesting. Well, okay, heart. Most medical. Now, the one that I want to highlight first. Now, with this one, we are kind of foraying into our future topic called respiratory system. So, pulmonary blood vessels are the ones that collect oxygen from the lungs. That makes sense. Now, I'm just thinking how to ask you this question. There's going to be some areas of the lungs that will have more oxygen. Does that make sense? So let me ask you this. Keep it in mind that the function of pulmonary blood vessels is to collect oxygen from alveoli, from the lungs. What do you think is going to happen to the amount of blood that will get to the areas of the lung that are more oxygenated? So more oxygenated parts of the lung, are they going to get more blood or less? More. And here we say that less oxygenated. That makes sense? So in pulmonary, it is what we can call inverse metabolic. So higher oxygen, higher blood flow. Does that make sense? We're going to talk about it again, the respiratory system, as the perfusion, ventilation perfusion coupling. And you're absolutely wrong. More oxygen, more blood to pick up. Clear? Great. And that's the most exciting. In brief, you can say myogenic mostly, sometimes medical. Now, let me explain how myogenic regulation in the brain. Okay, so we're talking about, first of all, the myogenic regulation in the brain works in the specific range of pressures, which is basically from the low normal to high normal. Mean arterial pressure of 50 to mean arterial pressure of 150. So mean arterial pressure of 50, is that hypertension? Most likely. Like somebody's not like dying hypertensive, but pretty hypertensive. Does that make sense? Mean arterial pressure of 150. Is that hypertension? Absolutely. Is that like you're gonna die any minute, hypertension? Probably not. That makes sense? So you can easily develop mean arterial pressure of 150 just by exercising really hard. Okay, now this is how it works. Your brain is the most important organ in the body. Do you agree? You have to maintain a proper blood flow all the time. If it goes too low, what's going to happen? The blood flow through your brain starts to decrease. Well, not right away. What's going to happen first? Did you ever experience when you like work, when you sit and work like do something on the floor and then you stand up really fast? What happens? You get dizzy, you get lightheaded. You can black out, you can faint. It's called orthostatic pressure. Your cardiovascular system just doesn't have time to properly redirect and increase blood pressure in the brain. Yeah, your blood flow decreases, you get lightheaded, you can faint. Make sense? Mm-hmm. Yeah, it's not a problem. Pretty easy. Okay, does that make sense? So you need to, and if you supply too much blood to the brain, that blood vessels in the brain will start to leak. It's like, trying to, if you will try to put an amount of water that goes out of a fire hose into your shower, it can explode, right? So you need to maintain it very tight. Now, this is your blood vessel in the brain, okay? Look. And pressure starts to increase. What's going to happen, like, to the stretch? An increase. And what's going to be the response? What's going to be like the response here? Raising, constriction. So it will maintain focal block. Does that make sense? So basically, you can say that when the blood pressure goes up, the diameter of the blood vessels in the brain, it progressively goes down to maintain constant blood flow. Does that make sense? If you go over that 150 mean arterial pressure threshold, response cannot happen anymore. It's too high of a pressure. And basically, the constriction will give in to the pressure, and the blood vessels will start to rapidly stretch out. Now, basically, you can forget about that part. So as blood pressure goes up, what happens to the stretch? Goes up. What happens to the diameter? What happens to the blood flow? Goes up. And it keeps on increasing as blood pressure climbs up. And when you have such an enormous blood flow, the blood vessels in the brain start to leak. You develop brain edema. Does that make sense? The other way around. When blood pressure drops really low, what happens to the stretch? Decreases, diameter decreases, blood flow subsides, and your brain shuts down. That makes sense? So in the normal range, it's proper myogenic response. But when you get out of that range, you're done. Either of brain edema or you go into coma because blood vessels shut. Does that make sense? Yeah, that can happen. That can happen. That may be because if they hold their breath, again, they develop short-term acidosis, which can, in short-term perspective, inhibit the activity of neurons. Okay. Questions on this one? Okay, now we're going to talk about a concept. It's called Capillary Exchange, which just kind of, be attentive. Okay. This is a capillary. Okay? This is arterial end. So basically here is the arterial, okay? So blood flows essentially in this way. It's blood flow. Okay? This on the right is venular artery. That makes sense. And now we're going to talk about the pressures. So the first pressure, now blood flows. I'm going to ask you some pretty stupid questions. Blood flows. Does it push on the walls of the capillary? Yes, it does. It creates a pressure that drives fluid out of the capillary. Does that make sense? So we call it capillary hydrostatic pressure, HPC. Capillary hydrostatic pressure. And it goes on, what? That makes sense. Now, this capillary hydrostatic pressure, what is it? Like, what systemic parameter is essentially capillary hydrostatic pressure? What do we call a force that pushes on the walls of the blood vessels? What we're talking about. Yes. That's the blood pressure. That makes sense? Basically, it's equivalent. We can put it in parentheses. Does that make sense? Now this here, this one, this tissue. They're fluid in tissue. Yeah, extracellular fluid, right? Now, does it exert? Well, I should say extracellular interstitial fluid does not exert any pressure that drives fluid back in the capillary wall. Because in physiologically healthy person, all excess fluid in the tissue moves into the lymphatic system. So we can still put a little tiny arrow here saying hydrostatic pressure exerted by interstitial fluid, but it's going to be essentially zero. Are you with me? We just we acknowledge that it potentially can exist, but it is zero. Now, remember what osmosis is. Osmosis is the movement of water towards a solid, right? So the most abundant solid in the blood, in the plasma of the blood, is protein albumin. So albumin in the plasma draws water towards itself. Are we clear? So albumin pulls water back into the blood. Okay? We call it osmotic pressure. And since this albumin is in the capillary, we call it capillary osmotic pressure. Are we clear? Is there protein in the interstitial? Yeah. There's a little bit, not a lot, a little. Okay, does that make sense? So there's going to be a little bit of pool of a protein in the interstitial fluid. It's going to be pulling water from the blood back into the tissues, just a tad. Okay. Now, kind of summary. So look at the capillary. The blood pressure pushes the fluid out, while albumin pulls the fluid back in. That makes sense? in terms of interstitial fluid, there's no hydrostatic pressure, and the protein in the interstitial fluid pulls the water towards the tissue. Are we clear? Now, when you combine all those pressures to calculate the resulting rate, it is called net filtration pressure. So what is net filtration pressure? Just in general as a formula, okay? So let's assume, look here, let's assume that this direction is a positive one. That makes sense? So it's going to be hydrostatic capillary pressure, right? Minus osmotic capillary pressure. Does that make sense? Plus osmotic interstitial fluid pressure minus this one. Good? Now, this is 0. We can disregard. That makes sense? So let's write down what is NFP on the arterial line. So I know the numbers, so I'm going to tell. Hydrostatic capillary pressure is 35. It's all millimeters of mercury. Okay. Osmotic capillary pressure is 26. And osmotic interstitial fluid pressure is 1. Figure it out. That's arithmetic. Go ahead. Do the math. No, not minus 27. It's plus 1. 35 minus 26 plus 1. So 36 minus 26, what? 10. These 10, look, listen up. It's fine. Listen up. We decided that this direction is positive, right? So net filtration pressure on the arterial end drives the fluid from the blood into the tissue. Does that make sense? Look at the venular end. Look. What is the only parameter here that is changed? Okay. Albumin concentration in plasma, does it stay the same? Yes. Concentration of protein in the interstitial fluid, does it stay the same? Yes. The only thing that changes as you go along the capillary. Remember what we were talking about the whole day today? Blood pressure. Blood pressure becomes low. Does that make sense? So the only parameter that changes is capillary hydrostatic pressure, and that is 17 minus 26 plus 1. It should be negative. Minus, negative. All it means is that this time, since this direction is positive, on the venular end, fluid moves back into the capillary. Does that make sense? So on the arterial end, 10 drag the fluid out, and on the venular end, 8 drag the fluid in. Does that make sense? Fluid leaves capillary at the arterial end and goes back at the venule. Good? Now, as you can see, 10 isn't equivalent to 8, which means some of the fluid stays in the tissue. Well, it's strictly speaking, doesn't stay in the tissue. It flows through the tissue into the lymphatic system, and it works pretty much the same way as you would be using a hose to wash the dirt from the driveway. Does that make sense? The flow of water through the tissue will remove debris, dead cells, microorganisms, and wash them into a sewage. Does that make sense? Which is lymphatic system. Are we clear? Good? And that sewage is what makes this pressure zero. That all excess water constantly flows out. And then lymph is collected and goes back into the blood, and it's all fine. Okay? So we're not losing anything. It's just kind of, like think of your lymphatic system as that sewage and water treatment plants. Okay? Now, let's play with pressures. First, we're going to look what happens if somebody has hypertension, high blood pressure. Okay? If a person has high blood pressure, which parameter is going to need to change? Let's say, how about 1 millimeter of mercury? Sounds good? What you got there? What you got there? What's the difference? 4, right? It was 10 and 8. So the difference was 2. Now we have 11 millimeters that push the fluid out. Only 7 that return it in. So you're going to have more fluid staying in the tissue. More fluid staying in the tissue will produce what? Fluid in the tissue. What do we call it? Huh? Well, what your tissue is going to look like if you have a lot of fluid in it? More than normal. What it's going to look like? Yeah, edema, right? Make sense? So people with hypertension may have peripheral edema. Does that make sense? Can you do something about it? Can you increase another level? That's kind of 4 out of 10 questions. Can you artificially increase one of the parameters here? In a very soft way. So you need, can you do something about it? Can you do a compression soft? Does that make sense? You will artificially increase this parameter, and you will be able to return fluid back here or in the lymphatic system. Does that make sense? This is how you treat edema. You just put some pressure. Make sense? Now we're going to try something really cool. So the organ that produces albumin is the liver. Okay? So imagine liver fails, and the concentration of albumin goes down. Which means when concentration of albumin goes down, it doesn't pull fluid back as much. So you still have your 35 from a normal pressure. But this time, osmotic pressure will be 25. What you got here? I'm going to spare you another calculation and tell you that here we're going to have more to say. So if a person has a liver failure, what they're going to develop? Peripheral. More fluid will stay in the tissue, and they're going to have edema. Does that make sense? Same story without writing it up. Same story would happen if you will try to imagine someone having kidney problems and albumin starts to leak from plasma into the urine. Does that make sense? People with kidney failure will develop peripheral edema as well. That makes sense? Good. So what you absolutely must be what I call for you, and well, you should be able to do. So if I tell you in a question, imagine you have a patient who's, and I will give you all the numbers, it's not a problem. But like, imagine you have a patient whose blood pressure is lower than normal, constant. Okay? How does it affect net filtration pressure on arterial end? If his blood pressure is lower, right? It's not 35, but 34. The net filtration pressure will be what? Lower. So I can ask you, what happens to net filtration pressure and which parameter is affected? Does that make sense? If I tell you, like, if we start to play with albumin concentration in the plasma, which parameter will be affected? Capillary osmotic pressure. Does that make sense? Do you understand what I can ask? So for instance, I tell you, what if we start messing with albumin in the plasma? Which parameter, which individual pressure will be affected? Capillary osmotic. How? If albumin concentration goes up, osmotic pressure, capillary osmotic pressure goes up. That makes sense? If albumin concentration goes down, goes down. Actually, have a question? Go ahead. Yes. It causes dehydration in the tissue. And you can actually, if you think about it, like, good example would be to say, let's reduce it from 35 to 34. What's going to be here? 9. And we reduce 17 to 16. What's going to be here? Negative 1, right? So basically, you have the same amount of fluid being returned, the amount of fluid that goes here. So you have pretty much no lymphatic flow, which means all that crap that accumulates in tissues stays there. That makes sense? And like, before we wrap it up, I want to kind of give you sort of cues on this whole unit. Please look at the regulation of everything. I'm going to ask a lot of questions on how does something change when cardiac output decreases, heart rate decreases, and diastolic volume decreases, venous return decreases, shit like that. That makes sense. And here, same story. So brain dump is your savior. You understand? Please make sure that you know how to do it. Very good. Any questions?